System design sounds scary until you realize it's just structured common sense plus a few core building blocks. In this video, I will walk through those blocks. If you understand these, you can reason about almost any backend system, interview question, or architecture diagram. Let's start with the most important idea. A system is just users sending requests to services that store and process data. Everything else is detail. So we break that picture into layers. At the edge, you have clients. Mobile apps, web browsers, other services, cron jobs, IoT devices. They send HTTP requests, gRPC calls, messages, or events. Those requests hit an entry point, usually a load balancer or API gateway. The load balancer's job is simple. Take incoming traffic and distribute it across multiple backend instances. This gives you horizontal scaling and fault tolerance. If one instance dies, traffic goes to the others. The API gateway adds extra features: authentication, rate limiting, routing to different services, and sometimes request transformation. Behind that, you have application servers. This is where your business logic lives. In a simple system, it might be one monolith. In a larger one, it might be multiple services. The application layer validates input, applies rules, calls databases, talks to external APIs, and returns responses. Now you need somewhere to put persistent data. That's your database. Relational databases like Postgres and MySQL give you strong consistency, transactions, and structured schemas. NoSQL databases like DynamoDB, MongoDB, or Cassandra trade some of that for scale or flexibility. For system design fundamentals, you need to know three things: read versus write patterns, indexing, and consistency. Reads: what queries are common? What fields do you filter by? Writes: how often does data change? In what patterns? Indexes: extra data structures that speed up lookups but cost memory and write speed. And consistency: how quickly writes become visible across replicas. Now scale. If you put everything on one database, it will eventually choke. So we add two tools: caching and replication. A cache is a fast, in-memory store, usually Redis or memcached. You cache hot data, user sessions, product details, timeline pages, or computed results. Reads hit the cache first. If there is a miss, you fetch from database and write into the cache. This reduces load and latency. Replication means having multiple copies of your database. A common setup is one primary for writes and several replicas for reads. Writes go to the primary, then changes stream to replicas. You point read-heavy queries at replicas to scale horizontally. The trade-off: replicas might lag slightly behind. That's eventual consistency. Now, what about background work? Not everything should happen inside request response. If a user action triggers slow tasks like sending emails or generating reports, resizing images, charging cards, you don't want the user waiting. So you introduce a message queue. The app publishes jobs to a queue. Background workers consume them. Some examples are Kafka, RabbitMQ, SQS, or a managed queue. Queues decouple producers from consumers. The producer only needs to know, I dropped a message, I'm done. Consumers can scale independently. If traffic spikes, you add more workers. Next building block, storage beyond the main database. For blobs like images, videos, PDFs, or backups, you use object storage. Some examples are S3, GCS, Azure Blob. Store files there and store reference to them in your database. Now let's talk about reliability. Real systems fail, so we add patterns to avoid cascading disasters. Circuit breakers. If a downstream service or a database is failing, you temporarily stop calling it and return a fallback. Retry with backoff. If a request fails, you retry a few times, waiting longer between attempts. And idempotency. Design operations so repeating them doesn't cause double effects. Rate limiting and quotas. Protect your system from abusive or buggy clients. Slow down or block requests after certain thresholds. Now, observability. If you can't see what's happening, you can't operate the system. You need three things: logs, metrics, and traces. Logs are events. User 123 logged in, or error connecting to database. Metrics are numbers over time, requests per second, error rate, or latency percentiles. Traces follow a single request across services. Together, they let you answer, is the system healthy? What's slow? And where are we dropping requests? And finally, some classic design trade-offs show up everywhere. Latency versus consistency. Do you return slightly stale data faster or slower but strongly consistent? Simplicity versus flexibility. Do you keep one simple service or split it for team autonomy? Cost versus performance. Do you over provision to stay ultra fast or accept occasional slowness? Remember, in interviews, you don't need perfect answers. You need to show that you see these trade offs and can explain your choices. So let's recap the minimal mental model. Clients send requests. Load balancers and gateways distribute them. Application servers handle business logic. Databases store state with indexes and replication. Caches speed up hot reads. Queues handle background work. Object storage holds blobs. Rate limiting and circuit breakers protect the system. Logs, metrics, and traces tell you what is going on. If you can draw that picture and talk through how data flows from left to right and back, you already understand more system design than many developers. Everything else, sharding, CDNs, leader election, consensus algorithm, are extensions on top of these basics. Master the fundamental first. Then you can add complexity when you actually need it.